part of the issue with this class, as I've mentioned a couple of times, is that I've never taught this class before, and so I have a really hard time of judging how long things are going to take. And so sometimes the content just kind of ends up changing. I ended up just putting together the slides mostly yesterday, and what this ended up being is slightly different than what I was like thinking we would do, which is I was thinking we would do piecewise models today, but I just still didn't feel like we had really gone far enough with Bayes, and so I just decided to kind of switch the focus to there, and specifically fitting Bayesian models for binomial outcomes. Okay, so we had talked about that last time, but we talked about it through a maximum likelihood framework and not a Bayesian framework. So I started to put together what I thought was going to be like the first half of the slides on that topic, and then I ended up just making it the entire topic. So today we're going to go through what I hope will be like basically a full application, like start to finish, and we'll go through 2 of them, okay, with 2 different data sets using Bayes and fitting a model with a binomial outcome, okay? If we have time, which we probably won't, then I do have some slides on missing data. Those are the ones that were giving me problems. So they're actually not currently in this slide deck, but they're rendering currently, okay? So the agenda, we're going to do our equation practice like normal. I do think next time, which will be our last class, I will do the equation practice again, but maybe I'll do what I just mentioned when I was talking with Chris. I'll give you probably more of like a verbal prompt, which would be like a research question, and then you can write the code for that, and I'll show you what I would have written for that same thing, okay? Then we'll go through these 2 walkthroughs like I was talking about. One is on Twitter data, the other is on lung cancer data, and then we'll talk about missing values if we have time, okay? All right, so we're going to start out with some equation practice. So please read in the nurses data set. This is a new data set that is on Canvas. So tidyverse, and then just read in nurses, okay? Okay, so it should look like this. So we have a hospital, we have a ward. The wards are nested in hospitals. So we have this ward ID, which is a unique one, which is sort of just these 2 things stapled together, okay? And then we have a nurse. So each row in this data set represents a nurse. We have their gender, their experience, their stress level, which is the outcome. And then we have the ward type. So that's a ward level variable, the size of the hospital, and then this XCon thing, which is the experimental condition, okay? I don't know what the experiment was, but there was some experimental condition. Okay, so using that data, try to fit this model, please. Okay, so in this case, we have an intercept that is randomly varying at this J level. That J level is ward ID. We have a coefficient for experience, which is also randomly varying at the ward ID level. And then we have a ward type as a predictor of their intercept and the slope. Okay, so that's going to look like this. We have experience times ward type. So this is the main effect of each of these plus their interaction. Okay, so this is the main effect of experience, this is the main effect of ward type, and this is the interaction between ward type and experience. And then we have experience randomly varying at the ward ID level. Okay, this one below is the same thing. Okay, so this part expands out to this part. Okay, and so those are 2 different ways of doing the same thing. Okay. All right, now go ahead and try to fit this model, please. Okay, so in this case, at our level 1 is the same as before, except we now have the intercept and the slope for experience randomly varying at the ward ID level and the hospital level. Okay, and then this part is the same as before, but now we have this additional hospital size variable. Okay, and we have 2 coefficients, but it's actually just 1 variable. So it's 1 variable with 3 levels, small, medium, and large. And so we just add that variable in as a factor, and it will add in 2 coefficients for us, with the third, this one, being the reference group. Okay, so that ends up looking like this. We have experience times ward type, so that's all of this part. Okay, and then we have plus hospital size, so that's these two coefficients. And then for both of these two coefficients, they're randomly varying at the ward ID level and the hospital level. So experience is randomly varying at ward ID plus experience randomly varying at hospital. Okay? All right, let's try this one. Okay, now at level 1, we're also adding the additional age variable. Okay, these two coefficients are still randomly varying at the ward ID and hospital level. At the ward ID level, we now have experimental condition entered as a predictor, and we have no predictors at the hospital level. But notice here we also have the off diagonals set to 0. Okay, so we're not estimating the covariance there. So here's how we would do that. We have Experian, right? This one, intercept and slope, both randomly varying at both levels, so they're here and here. But then we use this double bracket or double bar to note no covariance. Okay, so just the variances. So we do that, and then we also have age, which is here, and then experimental condition, which is here, because the experiment was conducted at the ward level. Okay. All right, this is an alternative syntax down here too that does the same thing. All right, let's try this one. Okay, here we have intercept and slope for experience, randomly varying at both levels. We have age again, but now we have ward type entered as a predictor at the ward level, and then we have hospital size entered as both a predictor of the intercept and a predictor of the slope for experience. Okay, so that's going to look like this. We have experience times hospital size. Okay, so that's what the main effect here, and then the interaction here, plus the main effect here. So this is all of that, just this part. Okay, and then we have age, which is there, experimental condition, which is there, and ward type, which is there. Okay, these things are randomly varying at the ward and hospital level, so that's the same thing here that we've had before. Okay. Oops, wrong button. Let's try this one. This one is quite different, so take your time on it. I'm giving you 3 minutes rather than 2 minutes. All right, in this case, we now have experimental condition specified as the outcome. Okay, and we would potentially want to do this in reality to see if the probability of being assigned to treatment or control depends on specific conditions. So if we have random assignment, we probably don't care about this because that's going to theoretically take care of that stuff. But if we don't have random assignment and we have some quasi-experimental design, so like maybe we're doing a regression discontinuity or something like that, then we might want to actually do this, where we first model the treatment condition to see if the probability depends on observed characteristics of our sample. Okay, so here we're specifying experimental condition as the outcome. So that's going to be generated from a binomial distribution with some unknown probability p. Okay, and whenever binomial has n equal to 1, that's the same as a Bernoulli distribution. So we could also write this Bernoulli p prob equals p. Okay, and then this is going to be modeled in this case just by age. All right, but we're going to allow age and the intercept, whatever our baseline log odds are, to randomly vary at the ward ID and hospital levels. Okay, so we have to do this sort of in 2 steps. To get this to actually model, we need experimental condition to either be a factor or to be coded as 0, 1. All right, and that's not how it was here. It was, I think, treatment and control, or experiment and control, or whatever. So I'm going to first redefine that thing to be a factor. Okay, then I'm going to fit the actual model, and notice I'm using Glimmer here now instead of Elmer. And then I just have this additional family equals binomial. I don't actually have to specify link equals logit because that's the default, but I like to do it anyway just to be very explicit. Okay, the rest of this is just like before. So we have age as a predictor, and we have age randomly varying at the ward ID level, and we have nothing randomly varying at the hospital level. So you can see alpha is JK, beta is just J, and then you can see we have alpha J and beta 1 here, and just alpha K here at the hospital level. Okay. Any questions on that one?
Yeah, I got an error about the data argument. I don't know if others did. I tried to Google it, but just formal argument data matched by multiple actual arguments.
Oh, yes, I have data in here twice, so that would be why.
Classic.
So you
Thanks.
just have to take one of those out, and it should be fine. I never end up actually evaluating these code chunks, so there actually is a possibility there's errors on these ones. So normally I actually evaluate the code as I'm running them, so there's no chance of errors, but there are in this case. The downside of that is that my slides sometimes aren't ready. Okay, let's fit this one now. That was weird. My timer went from 5 to 1 and it was stuck on 5 for a while. Okay, so in this case, we're just extending the previous model, right? So we have age here still, so that's the same, but now we have ward type entered here and then hospital size entered there. So this is just the same as before, but now we're just adding hospital size and ward type here. Okay, and then we have age varying by ward ID and then one hospital. The rest should be the same, basically. Okay.
I have a question on this one.
Yep.
This is actually on all of them. I seem to have like such a hard time with understanding why, for example, like age is, it seems to be like there's two ways to write something as a fixed effect in these models, and I'm getting really confused because age is being shown as a fixed and random effect, and so is, and ward type is only being shown as a fixed effect, but that confuses me and seems to be catching me up on every single one of these.
Okay. So whether it's random or not is in the subscript, right? So that's always going to be there. Ward type is just a fixed effect, but it's at a different level. So this is at the nurse level, right? Whereas this is at the ward level. Does that help? I'm not sure.
I guess. I think I'm just really bad at this. Do you have more resources that would be like good practice besides your slides here? Because I could do these over again. I probably won't remember all of them going back, but yeah. I feel like I'm wrong so often.
So, I mean, my only other recommendation would be to look at the course readings, specifically the Gelman and Hill book. But yeah, I mean, it is just basically, you just have to look at the subscript to see if it's randomly varying or not. And then, you know, from there, yeah, if they don't have a J or a K or an L, if you have a 4-level model, then they're not randomly varying. So like alpha is almost always randomly varying in these models, right? So it just depends on what level it's varying at. Alpha here is randomly varying at J and K. So there's alpha J and there's alpha K. Like you can look here too. That's the other thing, right? So if I start out here maybe with my random effects and I see beta 1J, well, then I can just go back to beta 1J and see the age is the one that's randomly varying there.
Okay. So do you not recommend, or do you recommend going through this like one line, write some code, then look at the second line, modify anything? Like what is your process when you go through this?
I would probably write all the fixed effects first, and then I would write the random effects second.
So you're just looking for a lack of subscripts first, and then you go in.
So no, because in Elmer, right, all I would do is say, okay, I'm gonna add age, ward type, and hospital size. Age, ward type, hospital size. Okay. Then I'm gonna go back and say, okay, are any of those randomly varying? And then I would see, oh yeah, I have J for age. And so J is the ward ID part. So I'm going to add age as randomly varying at the ward ID level. But then for the hospital level, I just have alpha K. So like, you know, the other thing is, so I would add all my fixed effects first, and then I would look at what is randomly varying. We have a ward ID level and a hospital level. And then I would see if any, like, what are the levels, I guess, not what's randomly varying. And then from there, what's randomly varying at those levels. So I see here, right, just by looking over here on the left side, I can say I have alpha j and beta 1 varying at the ward ID level. So that's going to be the intercept and the slope for age. And then I have alpha k randomly varying at the hospital level, which is just the intercept.
Okay, so if you had like a mu B1 without a J, that would be an interaction or just a second level effect.
Yeah, so it would just be a second, well, it would be an interaction, but this is where I've mentioned before that I think the multi-level model nature of it can be more hurtful than it is helpful, because anytime you have a cross-level interaction like that, which is what that would be, right? If you had a predictor here, like ward type predicting beta 1, that's a ward level predictor predicting a slope at the nurse level, right? So that is an interaction. It's a cross-level interaction, but an interaction is just an interaction. There's nothing special about it just because it crosses levels. The only thing is that if you look at your data at the ward level, that data, that variable is only going to change values with wards, right? Whereas the age variable would change values with nurses, which in this case is each row of our data set, right? So then it's just you're just modeling that interaction. It just happens to be a cross-level interaction. And so like the equation is almost, I think of it more as like conceptually, we're thinking about something at the ward level predicting the slope at the nurse level. So like theoretically, we think in this case that age might relate to the probability of being in the experimental condition, right? And then we're saying whatever that effect is of age, it's going to depend on ward type, because maybe, for example, in this special care ward type, everybody is really young. Like that's where nurses go to get started. So there's probably not going to be really much of a relation between age and the probability of being in the experimental condition if the nurses are in this special care ward type. Otherwise, we expect there to be a pretty strong relation, right? So that's an example of a cross-level interaction. And so that would just be, you know, in that case, you would just change this plus to a multiplication symbol, like to the star.
Okay. That was really helpful. I have one more question if we have time for it.
Sure.
Is that okay?
Yep.
Okay. So is the only way to get in front of the vertical bar, like to be a random effect, the only way to do that is the subscript? There's not another way? Because my brain keeps telling me I'm seeing you put them there sometimes without a subscript, and I'm just getting confused.
So it's going to be either a J or a K, or you can also just look over here on the left side, right? So this is what's randomly varying, the alpha J and the beta 1J. That's what's randomly varying at the ward ID level. So then you do have to walk those back over here and say, okay, well, what are those things, right? Alpha J is the intercept and beta 1J is the age. Okay, and then similarly here at the hospital level, you only have one thing, the alpha K. And so then you have to walk that back. What is that, right? And sometimes it does get really confusing because it does, like, this is pretty simple where it all goes back to level 1. But sometimes you can have things that are at level 2 that are randomly varying at level 3. And so that's where you'd have to look here, make sure that you've got it right.
Okay, thank you.
Yep. So let's try this one because, well, not this one. I think it's the next one. Well, let's try this one. Okay. So in this case, we have age. Let me go back here. We have age, gender, and the interaction between those two things. Okay, so we're going to model that. We also have ward type, and we have hospital size. Okay, when we're looking at the random effects, we have alpha J and beta 1J, and alpha K and beta 1K. So we have the intercept and age that are randomly varying at the ward ID and hospital levels. So this whole part is going to be specified here, age times gender, right? That's going to give us age, gender, and age times gender. Then ward type, that's going to give us this one. Hospital size, that's going to give us this one and this one because it's a factor. And then for our random effects, we have alpha J and beta 1J. So that's going to be the intercept plus the age slope, right? Intercept plus the age slope, randomly varying at the ward ID and the hospital levels. Okay, let's, yes, we have one last one. Let's try this one. be careful on the random effects with this one.
Hey, Daniel.
Yep.
So would you talk a little bit more about like what research question these equations are asking? Because like in real world research, like in homework 3 in this class, we are asked to some research questions. We are not given these equations. Like, for example, model 7 and this one, I'm having a hard time to understand like what this model is and trying to tell us about this.
Yeah, sure, I can do that.
Yeah, thank you.
Mm-hmm. Okay, so I'm going to walk through the model first, and then I will walk through sort of what it's actually estimating. So we have the intercept randomly varying at the J and K level. So intercept here, right, at the ward ID and hospital levels. We have age and gender, and then we have experience, okay? And experience has J and K. Notice we have beta 3 here, not beta 1 or whatever, okay? So experience is the one that's randomly varying at these levels. So the first thing, like I said before, I would just go ahead and add all the fixed effects. So I'd add age, gender, experience, ward type, and hospital size. But for ward type, this is an interaction with beta 3. Okay, that's what that is when we have a predictor of the beta 3 slope. Okay, so we have ward type times experience, and then same thing with hospital size. We have hospital size as a main effect, but we also have hospital size as a predictor of beta 3, the experience slope. Okay, so that's going to end up looking like this. We have age and gender, then we have experience times ward type, and experience times hospital size. Okay, for our random parts, we have alpha j and beta 3. So alpha j is our intercept, beta 3 is experience, and that's randomly varying at the ward ID and hospital levels. Okay, so in terms of what this model is actually estimating, we're looking at the probability of people being in the experimental condition, right? So now we're saying the probability depends on their age, their gender, and their experience. Okay, those are sort of the nurse level predictors. We're also saying that the probability depends on the ward type. So I don't know what the standard one is, but it's probably like standard ward type and then special care ward type. Okay, this interaction is where it gets a little bit more complicated for interpretation, because this is a predictor of the experience slope. Okay, so again, we're saying whatever the relation between experience and the probability of being in the experimental control, that relation is going to depend on which ward type they're in. So again, maybe it's the same as I mentioned before, where all of the new nurses go to the special care ward type, and so therefore experience doesn't matter because there's very little variability in experience. So the relation between experience and the probability of being in the experimental control in the special care ward type is flat, maybe. This is what we're hypothesizing or what we're estimating. And then in the standard ward type, the relation between experience and probability of being in treatment control is very steep. Okay, so that's the interaction. There are different slopes for experience depending on the ward type. Okay, and then we're also saying that the probability of being in the experimental control depends on the hospital size. And again, the experience slope is going to depend on hospital size. So maybe in small hospitals, we're expecting there to be very little relation between experience, or it'd probably be the opposite, right? Maybe in small hospitals, you have a bigger range of experience. And so in smaller hospitals, you're expecting a really steep slope. In medium-sized hospitals, you're expecting the relation between experience and experimental control to be slightly less. And maybe in large hospitals, you don't really expect much of a relation between experience and probability of being in the experimental control. Okay, so this is a really complicated model because we have multiple interactions, but you can kind of see how it would all go together, right? We have these different ward types, we have these different hospital sizes, and then we have these main variables that we're interested in. But in this case, we're saying the relation between experience and the probability of being in the experiment or control group depends on hospital size or the ward type. Okay, that relation between experience and probability depends on those things. Okay, that's what the interaction is. All right, does that help? Any questions on that?
I have a
Yeah,
question.
that's really helpful. So, sorry.
Go ahead, Claire.
Okay, so I don't think I'm like understand 100% of it, but just to want to clarify this. In this possibility estimation, we only care about the fixed effects of age and gender, but we care about the interaction. So we care about the random effects of the interaction between experience and these two ward type and hospital, right?
Yeah, so basically, you're asking about the random effects now, right? And so for age and gender, we're going to say there's one slope. Okay,
Oh, yeah,
that one slope is assumed fixed across all wards and across all hospitals. All right, whereas experience, we're going to say is randomly varying. So that slope, you can think of it as like a massive interaction, basically. Experience has a different slope for every single ward, not ward type, but every ward and every hospital. Okay, and so then the ward type is predicting variance at the ward level. Okay, that variance at the between wards, that's what this is predicting. And then the slope variance here, we're predicting that slope variance here. Does that make sense? And then we have the same sort of thing going on at the hospital level.
Okay, I see. Okay, thank you. That's helpful. Really helpful.
Manuel, was that you that had a question too?
Yeah, I had a couple of questions. One was, I'm just trying to like think about like situations where you might end up with like a three-way interaction. So in this model, for the experience that's random, that has a random slope, if you had like an interaction of like word type with like, I don't know, like some type of like indicator of composition of ward staff, if you had that like level 2 interaction, then that means that you would have like a three-way interaction.
That's correct. So if we had another interaction here, like we had like some demographic variables of the ward type, and we're saying that the relation between that and ward type is going to also, we're going to model that also. So we'd have an interaction on this line that would technically, well, not technically, that would be a three-way interaction. You would have the interaction between ward type and composition and the interaction between those things and experience.
Okay. And for the previous model in model 7, where you had like a age and gender interaction, if ages varying randomly and you had like a predictor of like ward type as well for the beta 1, that interaction would only manifest with age, with the beta 1 age, or would it also apply to, I guess not, because beta 3 isn't randomly varying.
Yes, that's exactly right. So you figured it out as you were talking, basically. If we have something here as a predictor, it's a predictor of this, not of this, right? We would have to have beta 3. So if beta 3 were not randomly varying and we wanted to have something that was predicting this, we could. It's just that would then be a three-way interaction, right? There's the, again, like the multi-level part of all of this is really just like a heuristic. What you have is variables that are predicting something, and you have interactions among them potentially, and then you have distributions for your slopes or your intercepts that are basically where you're saying these are going to be different for every single one of these things. So very typical, right, is schools and districts. We say that we're going to have some intercept where kids start, and every school is going to have their own starting point, right? And that's like we're specifying a distribution for that random variance, and that's what makes it a multi-level model. But it's really not multi-level. Like, that's just a heuristic that is conceptual and is generally helpful, but sometimes can be a bit limiting because it's really just a regression model where we have some components of the regression model that are randomly varying across units.
Okay. And my last question is about how you do the modeling when you have like a nonlinear term. Like if you were to, let's say, transform age to a quadratic relationship, do you, and that's randomly varying at level 2, do you put both of those terms at level 2 as well?
So you would have, if you wanted to model a quadratic for age, you would have age like it is here, and then you would also have age squared in there. So you'd have to have both of them in there. And then you could specify them both as randomly varying at the higher levels if you wanted to. You will probably run into estimation issues though. And that is because what you would have is not only is like the trajectory randomly varying, which is like the overall kind of slope of the line, but also the rate of deceleration or acceleration. So maybe for some people it's linear, and for some people it's really curvilinear, right? So you would be allowing the degree of nonlinearity or the degree of curvature, because it's only one curve, to randomly vary between schools or whatever.
Okay.
So that's typically a really difficult thing to estimate because there's just usually not a lot of variance there.
Right. So then you would typically just have like the kind of linear term as or the random slope.
Yeah. So you would say we're going to have like the trajectory, overall trajectory, allow that to randomly vary, but the degree of curvature, we're going to make that fixed. Okay. So they're all going to have the same curve, but they're going to be like different slopes, basically.
Got it. Super helpful. Thanks.
Okay.
One more
other questions?
Nice.
Yeah.
Sorry for asking all of the questions today.
No, this is fun. This is good. We're just not going to get through all the slides today, but that's okay. This is good.
Is there any way to, or would you ever want to model a random effect that wasn't also fixed? Because in every example you've given us, the variable that is in the random effect, we are putting it in the fixed effect as well. And that has confused me. Sometimes I would be like, oh, this looks like this is random, but not fixed. Is that possible? Would you ever do that?
No. So that's a really good question. I should have clarified that from the beginning. You will only ever have random effects that are also fixed effects, because you have to specify it as like, here's the average relation. And then the random effect is how much does that average change across units.
Thanks.
Other questions? All right, so this is really good. We'll not get through all the slides today, but that's okay. We'll get through what we get through. All right. So today the hope is to get through 2 applied examples. We'll get through as much as we can, and then I don't know if we'll get through the rest next time or if we'll just move on. I really do want to cover cross-classified models next time, at least a little bit. And I'd really like to also at least discuss piecewise models, but we now only have 1 lecture left, so we'll see if we get through both of those. I will introduce cross-classified models at least, okay, I promise. Whether I get to the piecewise stuff or not, I'm not sure. Okay, so we're going to deal with real data, which I collected on Wednesday. It's from Twitter. I did anonymize it. You can see the code that I used to get it, and so you could actually go and replicate it and grab your own set of data if you wanted to, and that would not be anonymous. I chose to anonymize it because I just didn't feel real comfortable sharing a bunch of random people's tweets with you without their permission, although it is all public record, so there shouldn't actually be any problem with it. But also some of them, because of the topic, if you look at the most negative sentiment, were really, really awful. So I just omitted the text altogether. And what I did is I grabbed 18,000 tweets that all had the hashtag BLM, so Black Lives Matter. And then I, from there, coded the text in the tweet to be for sentiment, so positive or negative sentiment. And this is a really difficult thing because you have you know, basically people who are negative sentiment because they don't like the Black Lives Matter group. And then you have negative sentiment because there are people that are part of the Black Lives Matter group that are upset about things that are happening, right? So this isn't like necessarily a perfect indicator of, say, like political affiliation or whatever, but it's still an interesting thing to sort of try to predict. So what we're going to do is I ended up coding them for sentiment. I used the Sentimenter package, so it has some things where it will have these like valence shifters. So words within a sentence will change the valence of others, which will change the overall sentiment. So it analyzes sentiment at the sentence level. And then most of them have multiple sentences. So then I averaged that over the entire tweet to get an average sentiment. Okay. And then from there, final thing, I collapsed it to just say, is this tweet positive or negative? So if it was above 0, it's positive. If it's below 0, it's negative. Any of them that were exactly 0, and there were quite a few of them because they were just like, you know, very basic like news reporting stuff or whatever, like those, any of them that were exactly 0, I just removed. Okay. So so this is all that stuff I just said. I also ended up pulling out a few other features of the tweet itself. There's a bunch more in there that you could do if you wanted to, but I stopped at one point. So for example, you have the text of the description of the person. So when you're on Twitter, you can write your own description about yourself that's brief, right? So I looked for the word Trump in their description, okay? And so then that's a new like indicator that we can use in modeling, okay? So the data are on Canvas. I just put them up there this morning. They're also on the GitHub repo if you've been cloning or whatever. So I'll give you a minute or two, but please go ahead and actually read in the data. It's called BLM sentiment. And it basically looks like this. So I'll talk through it as you're kind of doing this. We have the user ID. This is anonymized because the user ID is a real thing. Status ID, which is also anonymized. So the status ID is the tweet level ID, right? Whereas the user ID is the actual user. So this is all of these rows 4 to 10 and beyond are all from the same person, right? From the same account, rather. And then the status ID is different for every row, okay? We have that Trump in description one, and then there's follower count, friend count, etc. Okay, there's a bunch of stuff in there. And I'll talk through more of this in just a minute, but I'll give you about 1 minute to get that data set read in. Okay, I think that is everybody now. So I'm gonna move on. Okay. So this is a data set that is mostly like any other data set. There's just one part of it that's a little bit different, which is one of the columns is called hashtags. And the number of hashtags used is going to vary by tweet, right? Some have one hashtag, which is BLM. Others have, you know, 7 or 8 hashtags. And so the way that these are stored in this data set is through what's called the list column. And I know some of you are familiar with list columns, but many of you probably are not. So if you look at that specific, like directly, you won't actually be able to see the hashtags. But what you can do is you can use this unnest function and then call the list column. Okay, so I say unnest hashtags, but what that's going to do is it's going to end up actually replicating a bunch of the rows. Okay, so if one person has, say, 6 hashtags, then that one row is going to be expanded to 6 rows, where the only thing that's different across those 6 rows is the hashtag. Okay, so I can't actually use that for like modeling, but I can use it to just look at these. So if I say unnest hashtags, I can then count hashtags and say sort equals true, and that'll give me a count of all the hashtags used and specifically like the order of their prevalence, right? So BLM, 2 BLM ones are the most prevalent, which is fairly obvious. We have Black Lives Matter, George Floyd, okay? So these are the most common hashtags used, all right? And if you do this on your local computer, you might also pipe this, I thought I had it on there, to view, because then you can look through the whole thing. And you'll see there's a bunch of other hashtags in there that are not specific to the Black Lives Matter movement that are pretty common in there. So we'll talk about that more in just a second. So we can use unnest to look at all of them, but we can't actually use that for modeling. So what we can do is we can pull features from that hashtag. Okay, and this is why we would look at the number of them, because we might look at that then and figure out which ones we think are going to be relevant for predicting whether the tweet was positive or negative. Okay, so let's pull some more features. The first thing I might want to do is just get an indicator of how many hashtags they used. Okay, and this is a fairly common thing that people do when they're trying to build models to predict whether an account is a bot or not. Okay, if you use a bunch of hashtags and you have like, 7 followers and you follow 2,000 people, then your likelihood of being a bot is going to be a lot higher than like other accounts. Okay, so maybe, probably not, maybe, who knows, maybe just the number of hashtags would also be relevant in predicting the positivity of these tweets, right? And so maybe we want to get that number. What we're going to do that is use this row-wise operation, okay? And importantly, every time you use this row-wise, you're going to want to finish it with ungroup, okay? So I would say row-wise, and then I'm going to say mutate. And now, because I'm in this row-wise sort of data frame, I can operate on this hashtag's list column just like I would any other column, basically. So I'm going to say, what's the length of hashtag? Well, the length is going to be, it's going to go into each row, because we're in this row-wise thing, and calculate the length of what's in that row. So for many people, it's just 1, but for other people, it's 3 or 4 or 5 or whatever. Okay, so I ungroup then at the end, and then I can say BLM select user ID and then hashtags, and then you can just see the number of hashtags people are using. Okay. More complicated is we might want to actually pull out specific hashtags. Okay, so for example, when I was looking through this, I saw one of the top hashtags, it wasn't in the top 10, I don't think, but it was like 12 or something like that, was Antifa. Okay, and so Antifa is not really related to Black Lives Matter like directly, but it is related, I would assume, in terms of that group, right? Like those things politically are like in conflict with each other, I would say, or maybe not directly in conflict, but certainly like the way they're discussed by the two different political sides are very different. So maybe we think that people that are using Antifa in the Antifa hashtag are going to be, like, I would guess people using the Antifa hashtag are going to be more negative in their tweets about Black Lives Matter than people who are not using Antifa in the Antifa hashtag. Okay, so I could pull out basically a dummy code to see whether or not they used the Antifa hashtag also, in addition to Black Lives Matter or BLM. Okay, so I'm going to row-wise here again, and now I'm going to mutate. I'm creating a new column, which I'm calling has Antifa hashtag. Okay, so that's just a dummy code. And then I'm saying any. So what it's going to do is, let's imagine that one person had 5 hashtags, right? What it's going to do is say, are any of those hashtags Antifa? Okay, and so it's going to go through, and I'm using grepl, which is a logical looking for this pattern in this. Okay, so I put this all in lowercase because I changed all the hashtags to lowercase. So then I don't have to worry about uppercase or lowercase. And basically this part of it, let's say there's 5 hashtags and the third one is Antifa. Okay, then that would give me in return, it would say false, false, true, false, false. Okay, so this any is saying, are any of those 5 true? And then in that case, it would come back, yes, one of them is true, so return true. If they're all false, then it'll return false. And so then I can say BLM count has Antifa hashtag, and we can see about 553 out of the 14,000-ish that we have left after I removed neutral sentiment have the Antifa hashtag. Okay, so that's one way we can pull more information out of this. All right, from here, if this were real, I would probably continue to do stuff like that, build up features like this is in the machine learning world would be called feature engineering. In our world, it's mostly referred to as just data cleaning, but like pulling more and more information out of this that I think is going to be relevant for my model building. Okay. Then I'm going to do some data exploration. Okay. So what I would do in this case is the first thing I would do is just look at the counts basically for my outcome. So my outcome is positive sentiment. Okay, that's what I created when I was creating my other one. And so you can see overall, there are more negative sentiment tweets than there are positive. And that makes sense given, I think theoretically, given what I said at the start, where, you know, the people are going to be tweeting negative sentiment with the hashtag BLM because they don't like that group and because they're outraged at what's happening, right? So there's sort of two reasons we could imagine the sentiment being negative for tweets that have hashtag BLM, right? And there's probably only one reason that we could think that the tweets would be positive for BLM, and that would be like people who are pro Black Lives Matter group, okay? So I also mentioned that Trump in description one. Well, what if I want to see from just a data exploration one if that relates to positive sentiment? Okay, this is kind of difficult because it's a categorical with a categorical, basically. You know, we have a yes/no with a yes/no. So there's lots of different ways we could do this. I think actually just looking at the counts like this is a good way to do it. So I just to make it a little bit nicer to look at down here, I changed my is positive sentiment from 0, 1 to positive negative. So if positive sentiment is greater than 0, then it's going to be positive. Otherwise, it's going to be negative. Okay. And then I'm counting Trump in description and sentiment. And then I'm going to group by Trump in description. So I'm grouping by here, and then I'm computing the proportion. So the reason I'm doing that is I want to see what's the proportion of positive and negative tweets when Trump is not in the description, and what's the proportion of positive and negative tweets when Trump is in the description. Okay, so I'm looking sort of within those groupings. And you can see when Trump is not in the description, right, about 58% of the time the tweets are negative. When Trump is in the description, we have now 68% of the time the tweets are negative. Okay, so that's giving us some indication that this variable might actually have some information about that. This is a way of looking at it sort of visually. This is still actually not ideal, but you can see for negative tweets, right? When Trump is in the description, this is a higher proportion, right? And then of the positive tweets, when Trump is in the description, there's a lower proportion. Okay. All right, the other thing that is worth doing, and I'm not going to do it right now because I would have to leave my slides and I just don't think it's worth it. But you can install this skimmer package if you don't already have it installed, and then you can run skimmer skim on your data set. And what's nice about this is it'll give you a quick overview of the entire data set. So it will tell you, it'll give you sort of summary information for all your different variable types. So we have 2 variables that are dates. We have, I think, some character vectors. We definitely have logical vectors, and then we have some numeric vectors. Okay, and it'll tell you sort of the ranges of those things, the counts of them, and it'll give you little spark graphs on the side that show you the distribution of your continuous ones. Okay, so if from doing that, I looked at them and realized we have a couple distributions, and it's not surprising, right? But there's a couple distributions that are highly, highly skewed, okay? Specifically ones like follower count, okay? The number of people that are following that account, okay? So I mentioned this before, but sometimes transformations can help with this, okay? And technically, we don't actually have to, so from regression, right, like just standard single level regression, our predictors don't have to be normally distributed, but our outcomes should be. And that's because our residuals need to be normally distributed. And that's not going to be the case if we're assuming a normally distributed model, and it's not. Okay. But despite that, if you can make your predictors normally distributed, or better approximate normally distributed, then you'll have an easier time with estimation very often. Okay, so I have, for example, entered raw data into models and ran into all sorts of convergence warnings, and it didn't really work. And then you just transform some of those predictor variables and it all works smoothly and you don't have any problems. Okay, so here's an example where we have followers count, which we're maybe going to use as a predictor in the model, but it's so skewed, and I know this is cut off by my timer here, it's so skewed that I think we're probably going to end up with estimation problems here if we just leave it as is. So what I'd like you to do is use this as sort of your baseline, okay? And then from there, try to apply transformations to this followers count and see if you can create something that looks more approximately normal, okay? Okay, so in this case, I decided to try a log transformation, and you can see the results of that are pretty dramatic, right? We go from this unbelievably skewed distribution to something that actually looks pretty normal, okay? And so again, this is not necessarily going to screw you up in terms of your results not working, but it will really help with your model estimation. And just having that part of it, like the computational side of it, be easier means that your results will probably actually be better because they'll be more stable and etc. Okay? But you just have to, if you do something like this, you have to make sure that you're interpreting the results at the end correctly also. Okay, so you would be interpreting the coefficient for this as a 1 unit increase is a 1 unit log increase in follower count, right? And if you want to get that back on the normal scale, you can, because you can just exponentiate any log and that'll put it back to the raw scale. Okay. Okay, account creation is another one. So in reality, like if this were real, I'd probably be doing data exploration for a while, like probably half a day, right? And I'd probably fit some preliminary models and stuff, but I'd be doing a lot of data exploration. But for now, let's just stop here. This will be like the last real one we do. Actually, there's one more after this, but I want to look at to see if I can find any relation between when the accounts were created and the sentiment of it. And the reason for this is, again, sort of relating to bots, okay? Because we know another very strong predictor of bots is when they were created. So if you have a bot that was created within the last month or the last week, and it's got all these hashtags and it's like put out 8 million tweets, but has like 7 followers and is following a bazillion accounts, that's really like high likelihood of a bot. And so here I'm just looking, I just have on that y-axis here whether or not the sentiment is positive or negative, and then I'm using this geom jitter to just actually lay the points over that, and then I'm adding a high degree of alpha. So you can see where it's darker on each of these, we have more accounts being created. So for some reason we have a lot back here, and then but then for both of them really we have more accounts being created here near the end. So I decided, well, let's just limit it to those that are created after January 1st, 2020. And we have a bunch of them, right? And you can see there's maybe a little bit of evidence that there's more accounts being created recently for the negative tweets than the positive, but it's not super strong, right? So there's maybe a tiny bit of evidence there. Okay, last bit that is part of modeling too, that is important for modeling, is the reason that we're doing all this and why we might think about doing this through a multi-level modeling framework is because we're interested in person level variance, right? So some people are probably going to overall just be really negative. Other people are going to overall just be really positive, and we want to account for that between person variance, right? And so that's where multi-level modeling will help a lot. But in this case, we only have tweets from the last 10 days, I think it is, or maybe it's a week. It's something like that, 7 to 10 days. Okay, so that means we have a lot of people that have only one tweet in the entire thing. Okay, So we might, again, consider including the number of tweets that somebody has as a predictor in the model. So we could actually calculate that, and that would be another predictor that we use. That would, again, be a really good indicator of maybe you're capturing bots, but maybe you're also capturing journalists, right? Because journalists tend to tweet a lot as they're covering stories, and maybe there's people out there that are covering Black Lives Matter stories, right? So they're using that hashtag a lot. So this is what that distribution looks like. We have a couple of accounts which you can barely even see, but that are just tweeting a ton, right? 200 tweets in the past week, whereas most of them are down here around 0. Okay, so most of them are probably between 0 and 10. Okay, but then we have a couple that are these sort of extreme outliers. So we could kind of just code these extreme outliers, have like another dummy code for them. We could also just include the number of tweets they used as a predictor. Okay, so this might end up seeming problematic though, right? If we're trying to estimate between people variance, and we have a lot of people that only have one tweet, well, then how are we going to separate their one observed data point from the between people variance? Okay, generally this is actually not a problem. I have a link here to a cross-validated thing that you can read more about this. But basically, if a person has only one observation, so it's like one observation per cluster, right? So you could think about this in terms of school stuff, like maybe there's only one kid in a school, okay? And that happens a lot when you have like students with significant cognitive disabilities, right? There might be only one student in that school that has that designation. So if you're trying to model between school variance for that group of kids, it might be difficult. But the thing is actually you're only going to be using information to estimate the between cluster or between people, in this case variance, when the n is more than 1. Otherwise, that's just going to be missing basically when you look at your random effects, okay? And so their estimate is just going to be their observation, okay? So this is theoretically not a problem, although it can end up with issues with estimation again, okay? All right, so now we've done our data exploration, and what we're going to do now is jump to modeling, okay? So this is all basically what I've said, but go ahead and try now to fit a model where we're just estimating the baseline log odds in the tweet being positive and account for between people variance, okay? Just go ahead and use LME4 in this case, and then we'll switch to BRMS here in just a second. Okay, so using maximum likelihood, that's going to look like this. Okay, I'm going to say library LME4, and then glimmer is positive sentiment. That's my outcome, right? And I'm going to just have the intercept as my predictor, and then that intercept is going to randomly vary across user ID. Okay, my data is going to be BLM, and then I'll say family equals binomial with link equals logit, and I get something that looks like this. Okay, so this is saying my baseline log odds of a tweet being positive is negative 0.4. Okay, and that intercept varies between users with a standard deviation of 0.95. Okay, and that's the variance in the log odds. Okay, so one thing we can do is BRMS has this function in logit scaled, which you can change the scale of it. That's why it's scaled. But by default, it's just 0, 1, which is what we want. So we can use that function on these values to transform them from the log odds to probability. Okay, so if I do that, I can just say fixed effect of M0ML, and I get 0.40. Okay, so there's about a 40% chance baseline that a tweet is going to be positive if it has the hashtag BLM. Okay, in terms of variability, we estimated the log odds, that negative 0.4 or whatever, to have a standard deviation of 0.95. So one way I like to think about these is to actually say, okay, well, what would it look like then for somebody who's 1 standard deviation below the mean, or 1 standard deviation above the mean, or maybe 2 standard deviations, whatever you want to do, right? So what I've done in this case is just said, okay, well, take my negative 0.40, that's my intercept, and then subtract 1 standard deviation. So somebody who's 1 standard deviation below the mean would have about a 20% chance of posting a tweet with a positive sentiment, okay? And then somebody who's 1 standard deviation above the mean would have about a 63% chance, according to our model, okay? We'll talk about plotting the variability. Once we get to the Bayesian part, then we'll take a break, okay? But I'm going to load broom.mixed so I can pull the random values. Then I'm going to tidy it, saying pull the random vals, give me the confidence intervals 2. And then I'm doing this mutate part just to change the level so that it goes from low to high, basically. Okay, so I'm saying reorder level according to the estimate. So it's just going to order them low to high. Then I'm going to create a plot. This is the basic plot right here. And then this stuff is just some theming stuff. But I'm going to say put estimate on the x-axis, put the level, so the person basically on the y-axis. And then I'm using geom line range here instead of geom error bar h. We could use either. Line range just doesn't have the whiskers at the end, so it's just a line, okay? And then x min is conf low, x max is conf high. I added some alpha to it, and then add a layer of points, okay? And then again, this is just some theming stuff. And we end up with something that looks like this. It's a little cut off on the sides, but you can see 0 is neutral, right? And well, it's actually not neutral. 0 is 0 difference than the main effect of negative 0.4, right? And then these are like the point estimates for each person. Notice for a bunch of these, we have this big straight line right here, and we have this big straight line right here. I don't know, but I'm pretty confident those are all people that have just 1 tweet, okay? And so all where we get like more of like a curve thing, those are where we actually have some variability, okay? So that's like what our variability looks like. And then next, what we're going to do is we're going to fit it with BRMS, okay? So we're going to take a break now, but when we come back, we'll do that, okay? And generally, I'll just say this before we leave, generally, you would probably just pick a framework to go with, maximum likelihood or Bayesian, and then go that way. In this case, we're just doing this so we have sort of a point of reference, okay? But the other thing is very regularly, specifically with like binomial models, you will end up with convergence issues if you try to fit it with maximum likelihood, okay? And so that's where using Bayes with BRMS or something else can really be helpful, because you can fit a whole set of models that you just can't fit well with maximum likelihood. Okay? All right, let's take a break for 5 minutes. Get my timer. We're actually not that far behind on that part. We are time-wise, but. Okay, see you in 5 minutes. What I'd like you to do now is try to just fit the exact same model, but using BRMS. Okay? So go ahead and give that a try. You can assume flat priors, so you don't have to specify any priors. Just basically use the exact same code you did with LME4, but use BRM with the BRMS package instead. Okay? And this will probably take a minute to estimate, which is why I've given you 4 minutes.
It actually took almost 6 minutes to estimate. So.
Okay, that's fine. All right, actually, just so we can get through more of it, I'm going to go ahead and just show you the code, and then you can have it running if you haven't had it running yet. Okay, so the main part is this first part. Okay, so all we have to do is just BRM. We don't have to, like with LME4, we have Elmer and we have Glimmer, right? For BRM from BRMS, we don't have to specify anything like that. Okay, it's always just the same function. What we do have to specify is the family. Okay, so we don't. I think it would be good to sort of always specify the family, but the default is Gaussian, which is normal. Okay, so if you're doing just like a normal regression model, you don't actually have to specify the family, but otherwise you do. And so in this case, we have to specify Bernoulli. That's just a BRMS thing rather than binomial. And again, a Bernoulli distribution is a binomial distribution when n equals 1. Okay, so we specify the family as Bernoulli with the link equal to logit. This part is exactly the same. This part's the same. And then this part is just to make the model run a little faster. So I have cores set to 4 because I have 4 chains. So having additional cores is not going to do any good. But specifying cores equal 4 means it'll run all 4 of those chains at the same time. Okay, so that's why you can see it goes chain 3, 4, 1, 2, 2, 4, 1, 3. Like it's just running them all concurrently. Okay, and then I also have this backend part, which is command stan R. I mentioned this before, but if you want to use that, it will speed things up for you. You just have to say install.packages and command stan R, and I put that code in the previous one because they recommend installing it from some other place. Once you have that installed, then you also have to run command stan R install command stan. Okay, and that's because it's going to install a different thing on your computer that's for the command line rather than R. Okay, and then you specify the backend like this, and then it'll actually call your terminal from your computer and run the program there and then bring it back, which is a little bit faster. Okay, it's not like, you know, gigantically faster, but it is faster. Okay, so after I do that, I can call a summary on this, and hopefully you got basically the same thing that I have. Notice the estimate of our variance is quite a bit different here. Okay, 1.51 as opposed to 0.95 that we got before. Okay, this is surprising to me. I did not expect them to be that different. But honestly, I would probably trust the Bayes model more in this case for 2 reasons. One, part of the real strength of Bayes models is estimating these variance components. That's sort of the thing there. That's part of the reason they're very often preferred for multi-level models. But also, we know with our data, right, that we have a bunch of people that have only 1 observation. And so therefore, we're probably stressing out our model when we're using maximum likelihood. And Bayes is better able to handle that. Okay, we don't have like the true answer here, so I can't tell you for sure which one is closer to the real estimate, but I would tend to trust this model more, assuming all of my model checks look okay. All right, so that's sort of the next thing we're going to do. The fixed effect is pretty darn close to what we had before, though. So first thing I would do is look at my posterior predictive checks. Okay, in this case, I'm saying type equals bars. The default is the density plot. Okay, and we saw that previously. But for bars, what we're going to look at is we're basically, again, what this is doing, a posterior predictive check, is it's grabbing one set of parameters from the posterior distribution and then computing predictions for every case in our data set. Then it's grabbing a second set of parameters from the posterior distribution and computing them again. Okay, so by default, it's doing that for 10 observations from the posterior distribution. And then we want to look at the characteristics of those predictions and make sure they match our observed data. Okay, that's what a posterior predictive check is. So these bars that's our observed data. So you can see why, right? That's our observed outcome. And this looks very similar to what we saw before, right? With our histogram, where we have more negative tweets than positive tweets. This Y rep is the repeated samples from the posterior distribution. And we put that as a point. And it's a point that has a line range on it, but it's so tight here you can't hardly see it. Okay, but what we would like to see is that point on there matches the bar, or at least the line range around that point is overlapping the bar. Okay, and that's showing us that we're doing a good job of sort of capturing our data. Okay, if that were not the case, that's an indication that your model is misspecified and you need to sort of revisit how you're building your model. Okay, and that might mean specifying a different family instead of Bernoulli. Maybe we want to do something else or whatever. Okay, or it might mean changing the way that you're coding predictors or whatever. We also probably want to do some convergence checks. So the first convergence check I always do is just look at this R hat value, right? and it's 1.00 here, which is perfect, and then 1.01 here. So I mentioned already that I think I would probably lean towards trusting this more, but 1.01 is not perfect either. Okay, so this is telling us that our chains, our multiple chains, had a little bit of difficulty mixing. Okay, it wasn't severe because anything above 1.1 is severe and to the point where we need to rerun things. But 1.01 is pretty good still, but it's a tiny bit of indication that we had a little bit of trouble mixing there. Okay, and so we could solve that by just increasing the number of iterations that we have, and that would probably fix it. But I'm not too worried about a value of 1.01 either. This is what our chains look like. Okay, so this is the density for our two things that we're estimating, the main two things, right? Our intercept fixed effect thing, and then our standard deviation, all right? And so you can see it does center around 1.5 here. And then over here on the right, we have our chains. Okay, so this is just the iteration history. This is the iteration after warm-up. Okay, so we've actually run these chains. We've run each chain for 2,000 iterations, but we just discard that first 1,000. And remember, that's because when we're doing this, they're usually starting in a random spot and they're searching around for a while. And so they're kind of really far off for the first little bit. Okay, and then they start to settle in a range, and then they're searching all around that range. And that's what we want to make our inferences off of, not those first samples where they're kind of jumping all over the place. Okay, and what we would like to see here is basically just a hairball like this, which is what it looks like, right? If we see any patterns or trends in there, that's a problem. And you can, if you look close, you can maybe see a tiny bit of like a pattern here on this one, which is probably why we're getting that 1.01 instead of 1.0, which is like this, where it's just like very clear that there's no pattern. Okay, so again, overall, I think this looks pretty good. All right, now let's say I want to actually start to make some inferences. I didn't show this before, and I'll show you a different way that we can do it also. But one way that's a nice way of getting your posterior distributions is to use this package Insight, which you probably already have because it's part of that whole Easy Stats suite of packages that we've used a little bit. Okay, so all we do is we load that library and then we apply this function get parameters to our function, which I've called M0B. Okay, and when we do that, we get the posterior distribution for our main effects. Okay, so like our fixed effects in standard regression. And so here's all the draws. If we look at this thing, it will have 4,000 rows. Okay, because we have 4 chains, each with 1,000 samples. Okay, so this is going to be all 4,000 of those samples. We can plot the density of that. So now this is a data frame. We can basically just pass it to ggplot just like normal, right? So we put the intercept on the x-axis. We call geome density. I'm specifying a fill color, this blue color. And then we put a vertical line where the x-intercept is equal to the mean of the distribution. Okay, so this pink line, which I probably should have made a little bit bigger, is the mean of the posterior distribution, but this also summarizes sort of our uncertainty around that mean. Okay. All right, so we can use the density for a bunch of different things. So let's say we want to know the likelihood that the intercept, the baseline log odds, right, is less than -0.5. Okay, so if we translate that to probability, we would be basically asking, what's the likelihood that the average probability of a positive tweet is less than 0.38? So we're saying we've estimated it at about 40%-ish. What's the chance that it's 38% or less, maybe even less than that, right? The maximum is 38%. Well, all we have to do in that case is take all of our samples and then count how many of them are less than 0.5, okay? Because that's what we're testing, right? Less than 0.5 for the log likelihood. We're going to sum all the values where that is the case, all those that are true, and then divide that by the total samples. So in row, I could also say just divided by 4,000 because I know how many there are. This is a little bit more programmatic though. Okay, and we get 0.069. So given our posterior distribution, which is right here, we're saying how much of this posterior distribution is below this value right here. So basically from this line over, how much of that, how much is there of that, right? And we find that about 7% of our samples are below this value. So if we wanted to know what's the probability that the real value is less than 0.5, given the evidence and our priors, which were flat, we would say it's about 7%. Okay, and again, this is one of those things that's very different in Bayesian estimation from maximum likelihood. We couldn't estimate something like that very directly with maximum likelihood, but we can with Bayes very easily by just using the posterior distribution and, you know, essentially counting or getting the proportion of samples in that range. Okay. All right. If we wanted to plot the person estimates, this is where I think it's better to go to the tidy Bayes package. Okay, and we'll be using the tidy Bayes package quite a bit here now for the rest of this example, but also the next example. And it's a general purpose tool for pulling all sorts of different things from your models. Okay, but it also has a lot of tools for plotting that are quite nice. So for now, we'll do the plotting ourselves, but then later we'll actually use some of the tools from this package for plotting. Okay, and the reason we have to do the plotting ourselves in this case is because there's not a tool that I'm aware of anyway to do the same sort of plot that we had before, that sort of like caterpillar plot, right? Using the existing tools there. Okay, so what we'll do is we'll start by saying, okay, what are the actual things that are in our model? And we do that by using, we first load tidy Bayes, and then we apply this function get variables. Okay, and it tells us there's this intercept. We also have the standard deviation of the intercept. I'm not sure what intercept is there, but this is our actual coefficient, B intercept. But then we have all these R ones, okay? R user ID 1, R user ID 2. And for all of those, they say intercept. That's because all we have that's randomly varying is the intercept, okay? If we had, say, a slope, so going back to our previous example where we had like experience as a random slope, right? Then we would have R user ID 1 intercept, and we would have that for every person. And then we would also have R user ID 1, comma, experience here, okay? So we would have basically the point estimate for every person for their intercept and the point estimate for every person for their slope, okay? And those intercepts and slopes are entire posterior distributions, right? They also, each of these things have 4,000 samples, okay? So that's part of why when you're thinking about like, wow, this model takes like 3 or 4 minutes to fit, or maybe it's like 6 minutes to fit. That's actually kind of amazing when you think about how many parameters you're estimating. You're estimating one for every single person, and then you're drawing actually twice that number. You're drawing 8,000 samples for every person. You're just discarding half of them. So you're doing a lot of stuff here, and you're able to get a posterior distribution for every single sample, okay? So R underscore whatever implies random. Those are the random variants, random deviations from the average, okay? So if we want to pull those, we can use gather draws, which is from tidy Bayes, or actually there's spread draws also, which will put it in a slightly different format. So I'll show you sort of the differences later. Gather draws is going to put it in a longer format. Spread draws is going to put it in a wider format. So here I'm saying where R user ID, and then inside of these brackets, I just put whatever I want the new columns to be called. All right, so I'm using ID to get the actual ID of the person. So if I come back here, this is the whatever is here, that's going to be what's stored in the first column. And whatever is here is going to be what's stored in the second column. Okay, so I'm saying ID, so that just 1, 2, 3, 4, 5, right? The ID of the person is going to be the first column, and then the term is going to be the second column. In this case, the term is just the intercept, and there's only one of them. So I could actually even just leave this blank, and it wouldn't show up at all. But so now I have the ID, we have the chain, the iteration from the chain, and then what they're calling draw, which I'm pretty sure is just the 1 to 4,000. Okay, so this iteration will go 1 to 1,000, 1 to 1,000, 1 to 1,000, 1 to 1,000, whereas draw goes 1 to 4,000. Okay, and then we have the variable, our user ID, and then we have the actual value. So this is the draw from the posterior distribution. Okay. Now we can compute credible intervals for these things. So there's multiple ways to do this, but what I've done is I've said, okay, group by the ID of the person. Okay. Then we're going to summarize, where I'm going to create a new column called probs, which is just going to be equal to median, lower, and upper. Okay. The reason I'm doing that is because that's the thing I'm going to compute in this next line, which I'm calling quantiles. And I'm going to compute the quantiles of dot value. Okay. The quantiles of dot value give me the 50th quantile, 50th percentile, basically, the 0.025 percentile, and the 0.975 percentile. So that's going to give me the median and the lower and upper bounds of a 95% credible interval around the mean or the median or whatever. It's the quantiles of it. Okay, when I call ungroup, it's going to now look like this. So we have 3 rows for each ID that have the median value, the lower and upper value of that distribution. Okay, I realize this is all super complex, both conceptually and in code. You have the code now for later, but part of why I'm walking you through this is because I want you to realize that when we're fitting it with a Bayesian estimator, right, everything is a distribution. So every single person has 4,000 draws that you can work with. And actually, when you ran it, it was 8,000 draws. And so then we can summarize those draws using tools like this. Okay, so then I can move it wider if I want, and we can plot. I'm just going to put the median on the x-axis and the ID on the y-axis, and then I'm using that geom line range again, lower and upper, and then adding the point, and then this is just plot stuff. And oops, I meant to not echo that. We get basically the same plot again. Okay, it looks a little different. It looks a little like more hairy here on the ends, and that's because of the random sampling from the posterior distribution, right? So if we look back at the maximum likelihood one, these were a lot more sort of clean on the edges because we're estimating them more like directly, but this is actually sampling from the posterior distribution. Okay, so that's a lot. So I'm going to pause just for a second. Do you have questions on that? Does that sort of conceptually make sense? Or if not, what's not making conceptual sense? Even if the code doesn't make sense. You can come back and just reference the code later if you want. Okay, so again, everything's a distribution. Everything that's estimated, you're getting samples from the posterior distribution for that. Okay. All right, let's extend our model. This one is again going to take a while to fit. So I'll have you start to fit it, and then I'll keep talking, and then you can sort of catch up after that. Okay. But let's add in the following predictors to our model. We're going to add in Trump in description. We're going to add in has Antifa hashtag, and we're going to add in the log of favorite count. Okay. We have to, though, say log of favorite count plus 1, because the log of 0 is negative infinity. Okay. So we have to add 1 so that they all have a value of at least 1. And the log of 1 is actually 0. So that will be fine anyway. Okay. And we have a bunch of them that don't have a favorite count. So we're going to do the log of favorite count plus 1. Okay. So you go ahead and try. I'm going to give you 1 minute. Just try writing the code. Don't worry about running the model. You can start to run the model if you want. And then you should be able to do other stuff down the line if you want. Just be aware it's going to take, maybe 10 minutes, maybe even a little bit longer. Okay. The code is going to look like this. We use BRM, is positive sentiment. Then we just add those predictors. Notice I can just add log favorite count plus 1 right here within the formula. Okay, so I don't have to actually do that calculation outside of the formula. I could if I wanted to, right? I could take my data set and say mutate and add a new variable that is maybe called log favorite count, which is just going to be exactly equal to that, right? But I can actually just put it in the equation also, and that works fine as well, okay? And then we're going to just allow the intercept to vary by user ID still. I'm not going to have these other things vary by user ID, especially because, in fact, none of these could vary randomly by user ID because they're all user level predictors. They're not tweet level predictors, okay? So then data's BLM, family is this, core is 4, backend command standard, right? You don't have to do this part, but this is just to make it faster, okay? So when I call summary on that, it now looks like this, okay? So our standard deviation of our intercept variance is about the same. Our intercept is actually pretty close to what it was, but now we have these additional predictors in the model, okay? So if Trump is in the description, so this is set to true, then on average, we're expecting the sentiment to be more negative, okay? Negative 0.36. And you can look at the credible interval for this, and you can see it's negative 0.74 to 0.01. So if you were to be in more of a frequentist world, and you got something like that, then you would say that is not significant. But we don't deal with significance in the world of Bayes. We deal with probabilities. Okay, so for me anyway, that would not be, I would not throw that out, especially because if you reran this model again with just like a different seed, so starting your random sampling in a different place, you might get a result that is now less than 0.0 or 0, whatever. So it would be fully negative. Okay, so this is there because there's uncertainty around all of this, and you've got random sampling and things too. So I would report this, and maybe it's not going to reach the same threshold that other people are comfortable with, and that's fine. But you're just reporting the probabilities that you're estimating. Okay. For has Antifa hashtag, we see that one is also negative, and that one is fully on the negative side, the credible interval, the 95% credible interval. The other thing is, I should have mentioned, 95% credible interval is fairly standard, but there's also quite a few people who push away from that specifically so that it is not interpreted in the same way that frequentists are. So a fairly common one actually is an 89% credible interval. Why 89% and not 90? I don't know, but that's a fairly common one. Okay. Finally, we also have this log favorite count, and that one's actually positive. So as there are more favorites for a tweet, the sentiment we're expecting to be a little bit more positive. Notice this is not a real strong relation though, because for every log increase in favorites, we're expecting the sentiment to increase by 0.05, or the log odds of a positive sentiment. Okay. And this credible interval is, again, like sort of right on that boundary-ish. Okay, so look at the R hats. Those are all 1.00. The R hat for the standard deviation is the same as it was before, 1.01. So posteriors. What's the likelihood of our posterior for the mean for the log of favorite counts being positive? Okay, so back here, we're estimating, so the mean of this distribution is positive, right? And so we want to know what's the likelihood of a positive effect. So whether it's 0.01 or 0.10, right? Just what's the likelihood that that effect is actually positive and not negative? Okay, so we're just looking at directionality here. What we can do is we can, again, use that get parameters for M1B, and that's going to give us a data frame that has all of our predictors. Okay, one of those columns is going to be called B log favorite count P1. All right, so that's the same thing it's called here. The log of our favorite counts plus 1. That's where the P1 comes from. Okay, and so we can count where those are greater than 0. we can sum all the cases where it is greater than 0, divide it by our total sample, and that gives us our proportion, which is 97. So we're saying there's a 97% probability that the directionality of this effect is positive. Okay, this is not, this would probably not meet significance from a frequentist point of view, though, because of two-tailed tests, right? So we would have to pass 0.975 rather. Okay, so so again, this is where like frequentists and Bayesians are just sort of different, and why lots of people end up, like myself, sort of railing against p-values. Okay, they have a purpose, and they're very good for that purpose. But I think, especially if you're in the world of Bayesian estimation, you should just be estimating the probabilities and reporting those probabilities. Because from my perspective, a 97% chance of the true effect being positive is a pretty high effect, right? That's a pretty high probability. So I'm not going to just discard that and say there's no information there, when I actually think there's a pretty high degree of information there, right? All right, you can also do marginal plots. This is just straight from BRMS, but it's pretty nice. You can say conditional effects, M1B, and then if you don't put anything here, it'll actually just give you sort of an interactive thing where you can just click enter, 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 and it'll just bring up more and more plots. But this is the marginal effect of Trump in prediction. So the effect of Trump in prediction, sort of holding the other variables constant, okay? And so here's our point estimate for true and our point estimate for false. So you can see the difference between those. You can also see that our 95% credible interval are overlapping by quite a bit, right? So we would probably want to talk more about the probability of that difference, which there's slides later on that sort of thing. This is for has Antifa hashtag. And then for our favorite count, if I do this, notice it actually detects, because we put the log part in the equation or in the formula, it figures that out, and then when it produces our marginal plot, it puts it back on the raw scale. So that's pretty spiffy, I think. And so here's our best estimate, like I think it's the mean of the posterior distribution, that blue line, and then the gray is, I believe, a 95% credible interval around that mean. Okay. You can also do, this is just an alternative view of it, but you can do what are called spaghetti plots, which is instead of doing that sort of cone shading, you can just actually draw a bunch of samples and plot each of those lines, so you can get a sense of the distribution of those lines. Okay. All right. As you were going through this, so I was playing around with a whole bunch of different models as I was putting these slides together. Sometimes I did run into warnings, and that was really easy to fix in this case by just doing the log transformation of follower counts. I was trying originally to not have us do that so that we could just interpret it more in a straightforward way of just saying, you know, as the follower counts, or at favorite counts rather, as favorite counts go up by 1, then this is the result or whatever. But I ran into warnings, so I ended up just log transforming that, and then that got rid of all the warnings. But there is a link here for more general guidance on how to handle warnings for models. So there's a bunch of different things, like you can change what's called the tree depth, and that's not going to actually change your model as much. It's just going to change the efficiency. So you need to go further on that to get your model to converge, and it's just going to slow down the rate at which it estimates. There's also this like adapt delta thing, which I don't totally understand, but you can increase that, and it'll basically spend more time searching around in the areas for the correct parameters. So you can check that out. There's quite a bit of it's pretty nice. It shows you here. I'll just go there real quick. It shows you, so if you're getting this warning, for example, then this is what you can do. Okay, so it's pretty applied rather than like super theoretical. Okay, all right, we have about 20 more minutes, so I want to get started with this second example, and we probably won't get through it all, but I'd like to at least start it. Okay, So, and again, there's more that we could do here. Obviously, we could continue on with the model, but we're just gonna stop there. In part because I think this is real data, which it makes it fun and exciting in some ways, but it's also not great for illustrating some of the examples because like it's hard to even find things that have a relation. All right. So we're going to go to a different data set, which is more of like a teaching data set. It's related to lung cancer. Okay, so what we're going to try to model here is whether or not the patient went into remission. Okay, so these are different patients that have lung cancer, and we have some information about them, and then we have whether or not they went into remission or not. Okay, so that's what we're going to try to model. So go ahead and read that data in if you haven't. And then we're going to build a model. Okay, so after you've read that data in, we're going to try to build a model where we have age, lung capacity, and tumor size all as predictors. And we're going to use those to predict whether the patient went into remission or not. Okay, but this is an important part here. We're going to build the model so you can evaluate whether or not the relation between the tumor size and the likelihood of remission depends on age. Okay, so whether the tumor size and the likelihood of remission depends on age or on age. Okay, so I'm not going to give you the full 5 minutes here because that would only leave us with 15 minutes. So I'll give you just 2 minutes. Just try to write the code. Don't worry so much about fitting the model. And then we'll talk about that. Okay. So I'll give you 2 minutes. So once this gets to 3 minutes, we'll start again. Okay, so going back to our data, we have age, lung capacity, and tumor size. Those are the 3 things that we're going to look at, right? And then we also want to test whether the relation between tumor size and the probability of going into remission depends on age. Okay, so that is an interaction. So this is how we would do this. We would say age times tumor size. So that would give us age, tumor size, and age colon tumor size, right? Plus lung capacity, and then plus 1 DID. So we're going to allow the intercept to vary between doctors, but all of these relations we're assuming are going to be fixed across doctors. Okay, yep, Chris?
Are we, every single time we do an interaction, always doing both main effects? It's like never going to not be that?
Yes.
Okay, just check.
Okay, so then the data is going to be HTTP and then family Bernoulli, cores 4, backend command stan. Okay, so the rest of that, oh, that should be command stan R. So it probably didn't actually run with that. So the rest of that, though, is the same. Any questions on that? Any other questions? Okay, so now we are modeling the probability of remission based on these things, and we're allowing the intercept to randomly vary across doctors. So we can call a summary on this, and we have this a standard deviation of our intercept of 2.01. All of our hats look good. We have baseline log odds of 1.66. Age is negative, slightly negative, which we would probably expect, right? As people get older, their likelihood of going into remission is reduced. Tumor size is slightly negative also. So as the tumor size increases, the likelihood of remission decreases. Lung capacity is slightly positive, but notice that most of the posterior, and actually for tumor size too, most of the posterior distribution is centered sort of right around 0. Okay, so that's evidence that those are not really very strong effects. And then for the interaction here, we get negative 0.00, and our confidence interval, credible interval, is negative 0.00 to positive 0.00, right? So we have a tight posterior distribution, but it is very much centered on 0. So this is probably not worth modeling at this point. And some of these other ones are, it's debatable whether they're worth modeling. Okay, so we can do our posterior predictive check. I'm doing bars again because we have a binary outcome, right? And that looks good. The points are basically lining up with with the top of the bars. And then we can look at our chains. We can look at our convergence here. So here's for our intercept, age, tumor size, lung capacity, and our interaction. We also probably have the standard deviation down there below, but it got cut off on the slides. But again, you're just going to want to look at these chains and make sure that they look like hairballs, that you don't see any patterns in them, right? So all of these look good to me. And again, you can also, these are the density of the posterior distribution for them, right? So you can see like age, 0 is over here. So most of the posterior density is negative. Whereas for tumor size, it's really kind of centered right around 0. And similarly for lung capacity and certainly for the interaction, right? This is 0.0015 and this is negative 0.0015. Okay. All right, but we can look at the marginal effects just like we did before. Conditional effects of LC with using age. And you can see that as age goes up, this is going from a 30-year-old to a 70-year-old, but that's a pretty steep relation, right? The odds of remission, or actually this is on the probability scale. The probability of remission decreases pretty steeply as age increases. For tumor size, it's similar, but you can see the slope is not quite as steep. And then for lung capacity, it's quite flat, which we would probably expect. And even for this one, right, it's steep, but we have a huge range of tumor sizes here. And so that may not be the most important predictor. All right, but this one is quite flat, probably could just get rid of it. For our interaction, we can also look at conditional effects like this. We just specify it like this: age, tumor size, right? That was the interaction we had actually modeled. And you can see, right, here's basically the one relation between age and tumor size. And then we've got 3 lines for different tumor sizes, but they're all basically identical, right? The slope is not different really for any of those. Okay. So that's a way to investigate our interaction. And all of this is telling us that this interaction is not worth looking at. We can also make predictions in a similar way that we make predictions with maximum likelihood. However, the difference is we probably don't want to just make one prediction because we have posterior distributions, right? So what we want to probably do is make X number of predictions all from our posterior distribution. Okay, so you could use your entire posterior distribution for all of your predictions, but that might be difficult too. So what we can do is using tidy Bayes again, we can first set a grid for the things that we want to investigate. So I'm going to say for age from 20 to 80, set the lung capacity at just the mean lung capacity, and then tumor sizes from 30 to 120. Notice I'm setting DID, the doctor ID, to -999. So that means I'm going to try to get population level estimates. So I'm going to say independent of any doctor, what do these relations look like? Okay. And then this is the tidy Bayes part. I'm going to say add fitted draws. Okay. The first argument to add fitted draws is the new data that you want to add the fitted draws to. And it's going to add them because it's going to add them actually to the data frame that you're passing it. Okay. The second argument is going to be the model, which I'm saying is LC, our lung cancer model that I fit before. And then we're going to say N, how many new samples do you want? How many predictions do you want? So I'm just saying 100 to make it relatively small, right? And then allow new levels equals true. So that's saying for this new level of -999. So that's just like we did before. It's just allow new underscore levels instead of dot. Okay. And what we end up with is something that looks like this. Okay. So we have age, lung capacity, tumor size. So these are all the combinations that we specified before. But then actually for each of those combinations, we're going to have 100 rows. Okay. 100 rows that are a random 100 rows from our posterior distribution. We get our draw, and then we get our dot value over here, which is cut off, but that's our actual value. Okay. So you can see we have now this data frame has grown from, I don't know what it was before, but to 555,000 rows. So this is a pretty big data frame at this point. And this is a really common thing with Bayes. When you're working with Bayes, you get data frames that have millions of rows pretty quickly. Okay, now we're actually going to plot this relation using tidy Bayes. Okay, so I'm going to say ggplot pred tumor. Okay, predicted tumor, that's this thing that I created over here, using the grid and then getting 100 samples for each combination of the grid. Put age on the x-axis, dot value on the y-axis, and then this is a function from tidy Bayes, stat line linear ribbon or line ribbon. Okay, and so what this is going to do is it's going to give me this line that is the sort of best guess mean. I think it's the mean, it might be the median, but I think it's the mean of those 100 draws. And then it's going to give you ranges for each of 3 levels. And you can specify the levels if you want. So 0.5, 0.85, 0.95, that's the default. Okay, so this is like a 50% credible interval. This is an 80% credible interval. And then the purple is a 95% credible interval. Okay, so that gives you a good idea of not just the relation, but also the uncertainty around that relation. And as we kind of would have expected when we were looking at the summary output from the model, there's a lot of uncertainty around this, right? The median or mean relation is pretty negative, but there's a lot of uncertainty around it. If you don't like these colors, you can also change the colors pretty easily. You can look at the documentation on how to do that, but it's just ggplot code. So you just say plus geom fill brewer or whatever you want to do to change the colors. Okay. Here's a slightly different plot. I'm using pred tumor and I'm saying filter where the tumor size is in 30, 60, 90, or 120. So I'm just pulling 4 values that are like sort of evenly spread across there. Then I'm putting age on the x-axis, dot value on the y-axis, and then I'm saying geom line where the group is equal to dot draw. So this is all the lines, okay? And then I'm saying alpha is equal to 0.2, so it's 80% transparent. And then facet wrap by these levels of the tumor size. And again, you can see there's not like a ton of difference. Higher ones probably more so, but that's part of why the interaction between age and tumor size is not big. Okay, couple more things here before we wrap up for the day. We also probably will care about the variance by doctor. Okay, what I just looked at was with doctor ID set to -999. Okay, so that's sort of the population level estimates for the doctor. But we probably actually really care about that variance in the doctors. So let's look at the relation between age and the probability of remission for doctors. Okay, so for the first doctor, what does that relationship look like? What does it look like for the second doctor, etc.? Okay, and we're just going to do a sample. So we're just going to look at the first 9 doctors, and that's because that makes it easier to plot. Okay, so what I'm going to do is I'm going to create a new object called pred age doctor, where I'm using expand.grid again to get the levels of the things that I want to investigate. Okay, for DID, I'm saying give me all the unique levels of DID, and then give me just the first 9 of those. Okay, if you wanted to, you could do this differently, where you just look at the levels of doctor ID and then just put them all in a vector like C, and then just hand enter each of those. This is a little bit more, quick, but whatever. Then for age, I'm going to say give me the age ranges from 20 to 80, and then I'm just setting tumor size and lung capacity at their means. Okay, so I'm just looking at the relation between age and the likelihood of remission across the first 9 doctors. Okay, then I'm going to say add fitted draws where the model is equal to LC and N is equal to 100. So give me 100 samples from the posterior distribution for each of these 9 doctors where the age goes from 20 to 80. Okay, so it looks like this. This is very similar to what we saw before, but now DID is going to change, right? This is for the first doctor for age 20. Then we would get another one for the first doctor for age 21, first doctor for age 22, etc., until we finally get to doctor 2, and then age 20, age 21, etc. Okay, and we're getting 100 draws for each of those combinations, so that's why we get almost 55,000 rows total. All right, now we can look at the relation between age and the probability of going into remission by doctor. Okay, so we have age on the x-axis and dot value, which is going to be our probability, on the y-axis. we add geom line, and we say AES group is equal to draw. So I'm getting different lines for every draw from the posterior distribution, saying alpha equals 0.2, so 80% transparency, and then I'm just going to facet wrap by DID, by doctor, okay? And so you can see there's a lot of variance here. If you have the first doctor here, your likelihood of going into remission is very low, regardless of your age. If you have this second or third doctor or this fourth doctor, your likelihood is much, much higher of going into remission than if you have this first doctor or the fifth or sixth doctor. Okay, so there's a lot of variance here. We can look at our variables again. So we have our DID now, right? And I'm going to get all the draws from the intercept. So I'm going to say spread draws. Oh, this is just for the intercept. So this is an alternative way. I'm going to skip past this quick because I want to get to the next part. This is an alternative to insight get parameters, just plotting our posterior distribution for the intercept. But what I really wanted to get at was the random effects. So here I'm using spread draws on LC, where I'm saying get all of the RDID, okay? And so spread draws just gives me a little bit different thing, where before, well, so RDID is here now, okay? RDID and term. All right, so here's all of my draws now for each doctor. And let's look at the first 75 doctors, okay? So I'm going to spread draws, LC, RDID. And here I'm just leaving this blank rather than giving it a term. It gives you basically the same thing. I'm going to ungroup that and then filter where DID is in 1 to 75, so the first 75 doctors, and then mutate to factory order it by the estimate. And then I'm just going to ggplot where I'm using geom density ridges, so I get something like this. Okay, so this 0 is going to be equal to the baseline odds, or log odds, right? And then these are the distribution for each doctor. So you can see for some of them, there's a lot of uncertainty, right? Like this is very flat. So it's not really very certain what the log odds are for that doctor. Whereas for others of them, like these ones, it's a lot more certain, okay? And this is a lot of them. You might want to do fewer to just get a better sense, but this is sort of like those caterpillar plots, but we're actually plotting the densities for each person instead, okay? We can also use gather draws like this to look at all of the sort of fixed effects and then look at the densities. This is sort of an alternative view to what we get from just calling plot on the original thing. But the last thing I wanted to talk about that I think is really important is these multiple comparisons, okay? And so this is where things are really different in the Bayes world, but I think really powerful as well, okay? So because we don't have to worry about adjusting alpha or anything like that. So we're going to quickly have a scenario, okay? We're going to imagine that we have a 35-year-old person who has a tumor measuring 58 millimeters, and they have a lung capacity rating of 0.81, okay? So we want to know what's the likelihood or what's the probability of this person going into remission if they had the first doctor versus having the second doctor in our sample, okay? So we want to know what the difference in that probability would be. So we're going to start out by grabbing all the fixed effects, okay? So there's multiple ways to do this. I'm doing it this way just because it's sort of the most by hand way, which I think is good to revisit every once in a while, right? So we have the intercept, age, tumor size, lung capacity, and then the interaction. So here's all of those, and it's posterior draws from all of them. So that's why we have 4,000 rows, right? 1,000 from each of the 4 chains, okay? Then we're going to get our data for our theoretical person. So I'm just creating objects here. And then from there, I'm going to create population level predictions, okay? So this is independent of any doctor. I have pop level. I'm just going to say FE, which is the thing I called this, fixed effects, even though it's fixed effects is a weird term when you're talking about Bayes. But I'm going to take my intercept plus the intercept times my age being 35, plus tumor size times tumor size, this thing, 58, right? Plus my lung capacity coefficient plus lung cap, 0.81, and then plus my interaction between those things, okay? So now I have this pop level. That's going to be 4,000, right? but it's my population level estimates, so independent of any doctor. All right, just adding all the fixed effects together. This is just like standard regression, right? So here's our sort of overall population estimate of, this is log odds of remission on the x-axis, okay? Now we're going to add in our doctor estimates for these two doctors, okay? So here's DID1 and DID2. We're just filtering DIDs, our full thing of all the doctors, where DID is equal to 1 and 2. And then I'm just going to say, add that in to the population level here, okay? And here. So we have now two objects, which are the predictions for each doctor, okay? We can put these in a data frame, and then I can do things like group by the doctor and summarize to give me the median. So here's the median log odds for the first doctor, and here's the log odds for the second doctor, the median of their posterior distributions. So those are pretty different. And we can actually plot the distributions like this, okay? So this is, given this person that we have, our theoretical person, this is our log odds of remission for that person, assuming they got the first doctor. If they got the second doctor, this is our estimate of their log odds of remission. So you can see that's a pretty big difference, okay? We can put it back on the probability scale as well. And this is probably a little bit more interpretable. The probability of remission is very low for the first doctor, and it's above 50% on average, like the median of the posterior distribution with the second doctor, okay? I know we're out of time, but just as a last thing, I want to show you, you can compute the difference of those distributions. We get 3.629. You can put that on the probability scale, okay? So there's about a 3% chance and a 60% chance with first versus second doctor. And if you exponentiate that, it'll transform it from log odds to just standard odds, right? I mentioned earlier that you can exponentiate any log and it'll put it back on the raw scale. So we get these things. And then if we calculate the difference of that, we get the odds of the difference. So this is 37. So this person, our theoretical person, is 37 times more likely to go into remission with Dr. 2 than Dr. 1. Okay, so this is super powerful information. And we can also actually compute the difference between those two things, between these doctors, by actually just saying Dr. ID 1 minus Dr. ID 2, we get a difference. Now we have a posterior distribution of the difference between those two doctors. Okay. All right, I know I'm 2 minutes over, so that's it for today. Yeah, hopefully that's helpful in terms of understanding why we might do Bayes and why it's different. Okay. All right, I will see you next week. Thank you, everybody.